To graph a function in polar coordinates, we need to shift our perspective on how functions work. We're used to Cartesian. Now in Cartesian, you specify an x, an input value, and what you do is you move left and right, and then you figure out what the output value is, the height. Well, in Cartesian, that's great. We've been training our brain to do that, but in polar, we don't work that way. The input values are angles. So what you need to do is you need to set your value of an angle, and then you sweep out along that angle by whatever radius you've been given from your rule. Then you sweep out another angle, and you put a dot wherever the radius takes you. You sweep out whatever your next angle is. You figure out the radius, you put a dot there, and so on and so forth. So we have to think of, in our minds, we have to think of spinning. And then what we do is we do that, for uncountably many points, and we play connect the dots. And then the pictures that we get represent the picture of the function in polar coordinates. Now, these functions don't pass the vertical line test. That's not something that exists for polar coordinates. And that's okay. What's important is that if you give me an angle, one angle, I will only be able to give you one radius value for that given angle. Now remember, you can sweep and have lots of different rotations. So you can rotate by 2 pi to end up in the same point in space. But because this is a function, you will only ever get one radius for the angle that you provide. So in our brains, we have to think of sweeping in a certain direction. The angles increase counterclockwise, and then we trace out where the radius is going to go. So the best way to take a look at this is to just give an example. So here's an example, 1 minus 3 cos theta. We're going to build a table of values, but we're going to combine this with what we call polar graph paper. So this is a polar graph, right? It's got radial values, rings for the radius, and then it outlines these common angle values. 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2 here, 7 pi over 4, and then back to 0 or 2 pi. So what we can do is we can go ahead and fill in this table of values given this function. So for example, if I put in angle of 0, the cosine of 0 is 1. So 1 minus 3 is going to be negative 2. So I know that for that very first value, when I have an angle of 0, so right along the polar axis, I should have a radial value of 2. So I have to go 180 in the opposite direction. So one radial unit is that first ring, the second radial unit is here. So this is when theta is 0. So now what I need to do is go ahead and calculate some of these other points. When my angle is pi over 4, then I go ahead and I calculate these values in this sense. So I will put in pi over 4 into cosine. I get 1 over root 2. So I'll get 1 minus 3 over root 2. And if you go ahead, you can take your calculator and you can crunch this number out, and it's going to end up giving you some value. So I'm taking my calculator out right now, and I'm going to crunch this through. And you can do a similar thing while we wait here, but basically the idea is that, okay, make sure you're in radian mode. You have to be in radian mode to get all these values if you need them. And if you go ahead and you calculate all of this stuff, you can get the values that you need. And so you can fill in some of the easy ones. The cosine of pi over 2. Cosine of pi over 2 is 0. You're going to get a 1 there. Cosine of pi is negative 1, so this is going to end up giving you 4. Cosine of 3 pi over 2 is going to be 0 again. And then once we go back to the beginning, we're going to get this value here. So in this sense, you can walk through. So I'm just going to fill in the rest of the values here for you. And when we go through, it should be straightforward. So going through, you should get about negative 1.12. Here, in quadrant 2, 3 pi over 4, this is going to give you a negative value. The cosine of 3 pi over 4 is going to be opposite in sign to what it was over here. So this is going to be about 3.12. This is going to be about 3.12 as well. And then this will be about negative 1.12. So yeah, you're going to have to sit there and fill in your table and calculate all these values, and that's fine. Again, a calculator can do that. It shouldn't be a problem. But what's important is that you take these values and you do something with them. All right, so here's what we get. When we have an angle of pi over 4, so along this line, our radius is negative once again, and we go ahead and we sit there and we calculate. Say, okay, along pi over 4, if I had a positive radius, I would stay in that quadrant, up here in quadrant 1. But I have a negative radius, so I have to go pi radians opposite. So I'm going to sit somewhere around here at pi over 4. When I'm at pi over 2, so when I'm at this angle here, now I have a positive radius, and my radius is 1. So if I play connect the dots here, what's happened is that I've started there, I'm sweeping through. As my angle increases to pi over 4, I make my way down there. As my angle keeps increasing to pi over 2, now this point has to somehow come up there. When I go to 3 pi over 4, my radius is a little bit bigger than 3. So somewhere around here, sweeping through right around there. When I get to pi, I have to be at 4, so I don't quite have the ring that I need. I'll go there. So it's a bit of a hack job of a picture, but you get the idea. When I go back to 5 pi over 4, I have a radius of 3.12. So again, I have a positive angle and I have a positive radius, so I stay exactly where this radius is telling me, where the angle in the same quadrant that I'm in. When I go back to 3 pi over 2, so this vertical line, I'll put a radial value there. When I get to 7 pi over 4, I don't want to stay on that axis. I have to go 180 opposite. And so I'll get to over there somewhere. And then finally, when I connect back, I'll have this picture. So what's happened is I've started here, I'm sweeping through, going up, coming back down, and going through here. And so we get this picture in blue, and you can see it's really interesting, right? You've got all these loops within loops. They would certainly fail the vertical line test, but that's not important. We no longer care about vertical lines when we're in polar coordinates. Technology can do this. A graphing calculator can graph this very easily. Software, something like Desmos, has polar graphing capabilities built in. So all of that can be greatly assisted by technology. But the simplest version of doing this is polar grid, polar graph paper, and a nice table of values. Now, other things that we're going to be interested in now will transition to calculus. So for example, if I take a look at this picture here, I can draw a tangent line. And if I draw a tangent line, it looks like, for example, there are some places where I have a vertical tangent line. And just for fun, I might want to ask, where is the tangent vertical? Or is the tangent line vertical? And this is going to require us to do some calculus. Now, we have talked about tangent slopes. And tangent slopes always come from a derivative. And in our particular case, a vertical tangent line, we know means that the slope is undefined. And in symbol form, that would be dy dx is undefined. Now, dy dx is going to be a problem. I can't find this if I have been given r as a function of theta. So what we need to do is use conversions and the chain rule. So we can assume there exists some way to represent this function here. So some big f of theta. Now we know that x is r cos theta and y is r sine theta. So really, this would be y of theta. Sorry, this should be f of x, so I apologize. And that would be then f as a function of x of theta. So I am now going to take a theta derivative of both sides of this expression. Chain rule is going to kick in here. I'm going to have a y prime of theta, and I'll have some f prime of x times x prime of theta. Well, this is exactly what I want. This is the derivative, and this is how we find slope. So the dy dx, which I'm calling this big f prime of x, is just going to be y prime of theta divided by x prime of theta. So it's very, very easy. If you are given x of theta and y of theta, which you can always find as r cos theta and r sine theta, then you can find slope. And these two things are easy because I will always be given my radius as a function of theta. Now, in the example that I was working on, 1 minus 3 cos theta, where is the tangent to the curve vertical? Well, this is my function. So the slope, the thing that I'm looking for, is from above here, y prime of theta over x prime of theta. So this is like saying, okay, I'm going to take the derivative of y, and then I'm going to divide by the derivative of x. Well, the derivative of y is like saying the derivative of r times sine theta over the derivative of r times cos theta. Well, r isn't really just a plain old r. R is 1 minus 3 cos theta, and that's going to be multiplied by sine theta. And downstairs, r isn't just a plain old r. It's a function. It's the function we have been given. And so this just ends up becoming a giant chain rule problem. And that's not a big deal at all. We can deal with that. So however you'd like to attack it is not a concern. You can FOIL everything out and take the derivative, or you can use the product rule, whatever is most convenient for you. So if I just go ahead and I differentiate the top by using the product rule, I'll get 3 sine theta times sine theta plus 1 minus 3 cos theta times cos theta. And downstairs, I'll get the same sort of thing. The derivative of cos is negative sine, so I'll get 3 sine theta cos theta, and they're multiplying. Subtract 1 minus 3 cos theta sine theta. And that minus sign comes from the derivative of cos. So it's a good opportunity up here to clean it up. You can't just leave it in the messy form that it's in. And so if I go ahead and I clean this up a little bit, this is what I'll end up with. I'll get 3 sine theta cos theta, subtract sine theta, plus another 3 sine theta cos theta. Now, I keep cleaning it up. It's not enough. There are trig identities that I'm going to want to make use of at some point here soon. But for now, I just group together these terms and I try to make it as neat and factored as possible. And really what I'm aiming for is a factored form. Now, upstairs, I'm not going to focus too much attention on upstairs because I haven't been asked anything about horizontal tangent lines. Horizontal tangent lines occur when I've got the top or the slope being 0. Downstairs, I have a common factor of sine, and that's important. That's what I'm going to take out of this. And so when I factor that out, this is what I'll get. Now, as we discussed, we will say the slope is undefined if the denominator is equal to 0. Well, the denominator has two parts, sine theta and 6 cos theta minus 1. The only way that the denominator can be 0 is if each of those factors ends up giving me 0. So it's either sine theta is 0 or 6 cos theta minus 1 is 0. We should know that sine theta is equal to 0 at 0 and pi. In this case, I'll have cosine equal to 1/6. Now that isn't a nice number. It's a strange number. And if you take your calculator, you can try to figure out exactly what that is, but cosine is going to be positive in quadrant 1 and quadrant 4. Now, if we think back to the picture of the function we had, it kind of had this loop-de-loop behavior, right? It started over here, swept up, and kind of did something like this. This is telling me that right at 0, I have a vertical tangent line. At pi, I also have a vertical tangent line. So that's right there. When I spin for these two, I should have one here and one there. And one of these angles corresponds to quadrant 1, and the other one corresponds to quadrant 4. So there's the quadrant 4 angle, and there's the quadrant 1 angle. And again, if you wanted to take your calculator, you could estimate what the value of this thing is. But from the picture, we are seeing that there are 4 places where we have a vertical tangent line. With a simple little bit of calculus, I can figure out exactly how to get the precise values of those. And it's a nice introduction to polar coordinates. Polars are indispensable. You're going to use them from this point on in all of your math and your physics. It is a really convenient way to describe things with rotation built into them.